Log on, tune in, find out. Another good idea from Cambridge.
This talk is in collaboration not only with him, but also with another person, namely with Alia Barakat. So the first thing I want to explain is the definition of a Poisson vertex algebra. And so the notion of a Poisson vertex algebra is kind of the Poisson algebra analog of a Lie conformal algebra. So for example, if you have a Lie algebra, you can define what is a Poisson algebra, which is a commutative associative algebra with a Lie bracket on it. And the same thing, if you have a Lie conformal algebra, you can define the Poisson algebra analog of the Lie conformal algebra that we are going to call a Poisson vertex algebra. And so the definition is the same as that of a Lie conformal algebra plus the notion of plus a commutative associative product. And in fact, the definition of a Lie conformal algebra was conveniently put in this blackboard by Victor. And so we keep the same axiom. And we say that I will change letter for some reason. A Poisson vertex algebra is a commutative associative, say unital differential algebra, and we denote by D the derivation of this algebra, together with a lambda bracket, which goes from V, tensor V, to polynomials in lambda, which we denote by curly brackets, but anyway, it's the same. Satisfying sesquilinearity, skew symmetry, and Jacobi identity, plus the usual Leibniz rules. Yes. Anyway, Carlian and square is the same. So the square brackets should be switched to curly brackets. In fact, this is the left Leibniz rule. You can also get the right Leibniz rule using skew symmetry. We have the right Leibniz rule that says that AB lambda C is A lambda plus D C B plus B lambda plus D C A. And I put an arrow here because what I mean with this arrow is that this D should be moved to the right, acting on B whenever we expand it as a polynomial. Okay. The usual
So we natural logic is left multiplication, right multiplication,
I don't understand.
Those algebras come
D is not
D is
D not compute.
minus D is
D is not
D
in
the
the
other
algebra.
way around. Minus D is D.
D is not contained in the algebra. It's an outer
It's
derivation.
a
Yeah,
derivation.
this is another derivation.
What means right.
Well, this is an endomorphism of the algebra. So you put it, so let me explain.
Yes.
A lambda B is a polynomial in lambda. So what does it mean? A lambda plus D B C with this arrow. By definition, it means sum for n which goes from 0 to n, Cn lambda plus d to the n C, where this d is acting on this element.
What's that funny symbol of the arrow?
Yeah, you can just forget about it and say that A lambda b is a polynomial in lambda.
And I thought that these minus d's were supposed to act on
Yeah,
the CNs.
exactly. Since here there is no arrow, this minus d is put on the left. But here, instead of putting it to the left, you have to put it to the right, this d. Because it matters whether you put it to the left or to the right. So this is with there. What does it mean? A minus lambda minus d b. With the same notation, this is sum minus lambda minus d to the n Cn. You see now d acts on the coefficients of the expansion. Well, here d does not act on the coefficients, it only acts on the right. This is why I put this arrow, not to forget to put it on the right. Just a notation.
Yeah,
Okay. Anyway, I was not even supposed to write this formula because it follows by skew symmetry, so it's not part of the axioms. And so the basic space on which we
So is it true that all this is just a compact way of writing ordinary Lie, well, in the first case, an ordinary Lie bracket, in the second case, an ordinary Poisson bracket? Or so, at least
for
it can-
some algebra from some Lie algebras of distributions. So
Or could I take this and blow it up into an ordinary Lie algebra? Just taking coefficients.
for Lie conformal algebras, yes.
Yeah, but what's
For Poisson, it's not clear.
Yes, any local function.
So as a side remark, this notion of a Poisson vertex algebra is the classical analog of the notion of a vertex algebra, whatever it is. It's obtained by putting quantum corrections to 0. And usually,
Excuse me, may I ask you a foreign question? This is this simply corresponds to Poisson bracket of the slot polynomial with coefficients linearly dependent on fields?
I didn't understand the question. Does this correspond to?
The algebra corresponds always to Poisson bracket, which are linearly dependent on fields.
Yes.
Yes, it's this is simply Poisson bracket linearly dependent on fields.
Yeah, I think so, yes.
Yeah, it is a special case if you take symmetric algebra.
No, this definition, in this definition is it involved that
It's
is
not
it-
necessarily linear.
This is
Lie conformal algebra is linear. Poisson vertex
so
algebra.
Poisson brackets leads to infinite dimensional Lie algebra in cases if it is a Poisson bracket with polynomial p, as Victor wrote, with coefficients linearly dependent on fields u.
Why linear?
U prime.
I think it always leads to Lie algebra.
But why linearly dependent?
Yeah, it's a special example.
If it's linearly dependent, yes, sorry, I didn't
Oh,
understand.
yes, only this special
If it's
case
linearly
is-
dependent, then it gives a Lie conformal algebra, namely Lie algebra.
No, I would like, it's my opinion is that it's exactly that class
Yeah.
which is understood.
When it's linearly dependent.
Poisson brackets linearly dependent on fields.
Yeah.
Like Gelfand and Dorfman, for example.
No,
or
but-
Astrid, yeah.
But Poisson vertex algebra is obtained from any field theory.
Anyway, he will write a general formula.
No, this special case under consideration is special class of Poisson brackets
Right.
whose coefficients are linearly dependent on fields.
That's a special case, when it's linearly dependent.
Right, this is what he wrote, yes, but later you will define Poisson. Yes?
No, my question is whether you consider all local Poisson brackets Or Poisson brackets.
No, I
linearly
consider all of them.
dependent on
I
field.
consider all of them.
All Poisson
Of
brackets.
course.
Simply all local Poisson brackets.
Yes, of course. So, and usually the space on which we define such a Poisson vertex algebra structure is what Victor called an algebra of differentiable functions. In the variables u1, ul. Namely, as he said, when we have partial derivatives, commuting partial derivatives. And in this case, in order to define, and we consider such an algebra of differentiable functions to be an extension of the algebra of differential polynomials. An extension of such algebra. So in this case, in order to define a Poisson vertex algebra structure on the whole space, it suffices to say what it is, what the lambda bracket is on generators.
It's a differential field, I said, yeah? Differential polynomials, you consider differential fields.
Yeah, let's say yes. It suffices to define the lambda bracket on generators, ui, lambda, uj, which are polynomials in lambda. Because then, if we know it on generators, we can extend it to the whole algebra using the axioms sesquilinearity and Leibniz rule. And the general formula is the following. If you take two elements, f and g in V, the lambda bracket will be given by the following basic formula. Sum over I and j going from 1 to L, m and n non-negative integers, dg, du, j, n, lambda plus d to the n, ui, lambda plus d, uj with the arrow, minus lambda minus d to the m, df, du, I, n. So this is teaching us that if we have an algebra of differentiable functions, in order to define a Poisson vertex algebra, it suffices to give a lambda bracket on generators and check on generators the axioms. Sesquilinearity you don't have to check because it's needed to extend it. You only have to check skew symmetry and Jacobi identity on generators.
Is on free jet.
Yeah, because we are assuming that V is an extension of the algebra of differentiable polynomials, so it's free. Let me name a few examples. The first example is Gardner, Fadeev, Zakharov, Poisson vertex algebra. So we take V to be the algebra of differentiable polynomials in one variable. And the Poisson vertex algebra, I only have to say what is u lambda u, so it's a polynomial in lambda, and I take the polynomial lambda. The second example is the Virasoro Poisson vertex algebra. This was already introduced by Victor. Again, we take V, the same algebra of differentiable polynomials in one variable. And now u lambda u will be u prime plus 2 u lambda plus c over 12 lambda cube. This is exactly the lambda bracket that Victor introduced for the Virasoro-conformal algebra.
Called Leonard-Magri bracket, yeah?
Or, yeah, in fact, I should have said Virasoro-Magri.
Leonard-Magri
we call
bracket.
it. Virasoro-Magri Poisson vertex algebra. The third example is the affine Poisson vertex algebra. So it's defined as it's associated to a certain Lie algebra with a symmetric invariant bilinear form and with a given element Pg. And then we define the corresponding Poisson vertex algebra on the space of differentiable polynomials in the elements of G.
This cubic term, is that the so-called central extension?
Yes, C is the central charge.
And does this give any reason for understanding that central extension? Or just this is a computation?
It's, I mean, it's exactly the same. As Victor explained, it's obtained by taking Fourier transform,
but
so it's just an equivalent
that
length.
lambda to the fourth wouldn't have worked.
Yeah, this is easy to check that it doesn't work with it doesn't satisfy the axioms. As for the Virasoro-Lie algebra, one...
Yeah, I just wondered if it gave
No, you can prove that whatever polynomial you take, it should be in order to satisfy.
So this...
Such polynomials.
So in this case, for the affine, the space is the algebra of polynomials in a basis of G, and I have to tell you what is the lambda bracket of two elements of G, and this is the commutator of these two elements plus the inner product of P with the commutator of these two elements plus hold on, no? Plus lambda times the inner product of these two elements. Okay, and in fact, one using the a simple remark, the Gelfand-Fadeev-Zakharov Poisson vertex algebra is a special case of the affine vertex algebra when you take one-dimensional Lie algebra, P equals 0 and UU equal remark G FZ is a special case corresponding to G equal one-dimensional Lie algebra with inner product to UU equal to 1. Okay. So this is a big class of Poisson vertex algebra, and starting from this, one can construct many more examples. For example, one can take what is called Hamiltonian reduction. Of the affine Poisson vertex algebra, and we obtain what is called the classical W algebra associated to the Lie algebra G and to an nilpotent element F. So here we can assume that G is a simple Lie algebra, for example. And then just to relate it to what we have seen these last few days, one can define for a Poisson vertex algebra, as for a vertex algebra, the so-called zoo algebra that Arakawa explained us a couple of days ago. And by taking the zoo algebra, what we obtain is the Zlotov's lies. It's the Poisson algebra on the Zlotov's lies, which is F plus E plus the centralizer of F. And then one can quantize this picture. Quantize this picture, and so if you quantize the Poisson vertex algebra, you will get what is called the W algebra. And if you quantize the Zlotov's lies, you get what is called the finite W algebra. And these two are connected by taking the zoo algebra. So this is what Arakawa defined, and this is what many people during this week discussed. And so what we are considering now is this object in this diagram, the Poisson vertex algebra. All right.
was a suggestion of Bernstein that somehow you can understand rigid orbits from the point of view of what orbits are obtained by adding one affine point to there's this algorithm of Dynkin that you add one more point to the Dynkin diagram and then you take sub-diagrams of that. So in the universe of affine algebras, you can somehow move around. You can move around from the standard orbits to more exotic orbits. So does this help in any way to have this affine guy above? In other words, does the affine guy living above tell you anything about quantum, about the algebras associated to Slodgy slices corresponding to rigid orbits? Is there any hope?
I'm not sure. I haven't thought about it. All right, so what I want to address now is what does all of this have to do with Hamiltonian equations? And there is a basic observation which is very simple. Which is the following. If V is a Poisson vertex algebra, then you can, and you mod out by the derivation. So as Victor said, this is called the algebra of the space of local functions. And the elements in this space are denoted by taking integrals. So by integral of f, I will mean the coset of f in the quotient space. So if you start with a certain Poisson vertex algebra and you take the quotient space, what you end up with is a Lie algebra. And I have to tell you what is the Lie bracket. By definition, this is the coset of the lambda bracket of f with g evaluated at lambda equals 0. And this is just a kind of very simple observation. It immediately follows by the axioms. Because if you look at the axioms of a Poisson vertex algebra and you put all lambdas to 0, well, Jacobi identity, when you put lambda and mu equal to 0, becomes the usual Jacobi identity for a Lie algebra. Skew symmetry, if you put lambda equals 0, does not become the skew symmetry for a Lie algebra, because you get BA equal minus A minus DB. So it's not the usual skew symmetry. But if you also put D equal to 0, namely U quotient by DB, you get the usual skew symmetry. Okay, so this is one part of the observation. The second observation is that V itself is a representation of this Lie algebra with the following action. The element of the Lie algebra acting on the function g is by definition the lambda bracket of f with g at lambda equals 0. This is well defined, and it defines an action of the Lie algebra. Also, this is immediate from the axioms of a Poisson vertex algebra. Okay. Okay, so now I have to tell you how to use this to define Hamiltonian equation. So first, let me remind you what is an evolution equation. on the algebra of differentiable functions V is just a system of equations dui dt equal pi of u, u prime, u double prime, and so on. And so, in fact, using the chain rule, you can get what is the evolution of any function f. This is sum for I, and then df duin d to the n times the nth derivative times the derivative of uin, and this is exactly the nth derivative of pi, which is exactly what Victor denoted before, the evolutionary vector field associated to p applied to the function f. Okay.
Yeah, because you forgot to say that pi is elements of V.
Yeah. And this is a general evolution equation. What is a Hamiltonian equation? Hamiltonian equation, I have to say, associated to a certain Poisson vertex algebra, structure on V, and to a certain local functional, which we call Hamiltonian functional. Integral of h in the quotient V mod dV. So when we have a certain Poisson vertex algebra structure, namely a lambda bracket, and a certain local function that we call Hamiltonian function, we associate to this data a certain Hamiltonian equation, which is the following: dui dt equal integral of h ui, where this is this representation. Namely, it's the lambda bracket h lambda ui at lambda equals 0. Or in general, df dt is integral of h f for every f. Okay. And
could you just remind us what this where this integral sends you?
the integral is just a notation for
This map.
the quotient map from V to V mod dV. Yeah, it's the quotient map from V to V mod dV, which sends f to the integral of f. And the reason for this notation is that we wanted the integral of the derivative of f to be 0 by the main theorem of calculus.
Your integrals don't look like integrals.
Ah,
It's a formal.
I should write dx.
Think of you, the symbol, you know. Exactly right.
Should think of u as a function on the circle.
No, just complain about this.
Right.
Okay, now that I told you what is a Hamiltonian equation, I can also tell you what is an integral of motion for such an evolution equation. An integral of motion is a certain local function. Which is constant in time. namely d with respect to the time derivative of this integral is equal to 0. And by looking at how we define the evolution, this is the same as to say that the Lie bracket of h and f is 0. So the space of integrals of motions is the centralizer of h in this Lie algebra. And so let me just say that we take such elements to be integrals of motion because in physics these are so-called physical observables, kind of local functions are the physical observables. And a certain Hamiltonian equation is said to be integrable in infinite degrees of freedom if you have an infinite number of integrals of motions which are compatible to one another, namely which are commuting with each other.
Sometimes, infinite could be different.
Yes, but we'll take this as our definition of integrability.
Well, that's not a very good definition.
It's not a good definition.
Of course, linearly
But
independent.
it is still bad definition.
Yeah,
because,
it's not clear.
Because if you take a direct product of two, tensor product of two vertex algebras, and take in one of them
Integrable
something
and
random,
not.
and one of them take integrable, and another one you take random. and
Yeah,
take
no, I agree.
some.
This is not the best definition, but we couldn't come up with it.
You should add some non-degeneracy or something,
Yeah.
Kind of completeness.
Yeah, yeah.
And completeness.
Plus some completeness. That we don't know what it means. If there exists an infinite sequence, integral of h0, starting from integral of h, starting from the Hamiltonian functions, integral of h1, integral of h2, and so on, which are all integrals of motions and which are pairwise commuting, namely such that the integral of hn and the integral of hn, the Lie bracket is equal to 0 for every m and n. Okay, example. Well, probably the most famous of all Hamiltonian equation is the KdV equation, so I will discuss that. This was introduced, I think, in the 18th century to discuss, to study fluid mechanics. And this is the following equation: du dt. The space is the algebra in one variable. And the equation is 3u u prime plus c u triple prime. And so the question is, this is an evolution equation. Can we write it as a Hamiltonian equation associated to a certain Poisson vertex algebra and to a certain local function? And the answer is in fact yes, and we can do it in two different ways. Hamiltonian equation in two different ways. The first one is by taking as the Poisson vertex algebra structure the GFZ and lambda bracket that I introduced before, and this local functional 1/2 u cube plus 1/2 c u double prime. Indeed, if you try to compute with this choice what is integral of h 0 lambda u with respect to this lambda bracket. It's a very simple computation, and you get exactly this 3u u prime plus c u double triple prime.
Lambda
Say it again?
lambda equals
At lambda equals 0. Yeah, I should have said
Okay.
comma. Anyway, lambda at lambda equals 0. And the second,
I don't understand. Why do you have the coset integral of h0 and then you have the lambda bracket? I don't understand.
yeah, you're right. Comma. This is defined here. So the action of a coset on an element is the lambda bracket evaluated at lambda equals 0. And the second, so this means that this evolution equation is a Hamiltonian equation associated to this Poisson vertex algebra and to this Hamiltonian function. And the second way to write it in a Hamiltonian form is by taking the Virasoro-Magri Poisson vertex algebra and the simpler Hamiltonian function, namely u square over 2. And again, if you do this computation, integral of h1 u with respect to this other Poisson vertex algebra, you get exactly the same answer.
But there are plenty of integrable systems which have infinitely many integrals, Lax space, everything, but the Poisson structure is not local.
Yeah, no, I'm not saying that
your construction.
Yeah, they want this.
I'm not saying that these
You're not
describes
saying
all
that you
evolution
can cover
equations.
this kind of system.
This is about local.
Yeah, we only discuss local.
Very exceptional.
Life is exception. So,
Supposing you didn't know the quarter big degrees equation, you guessed it from anything in this theory?
suppose you didn't know what?
Supposing you didn't know the quarter big degrees equation, could you have guessed its existence?
Oh, yes.
Just by looking at the
Yeah, there are
evolution?
many ways to produce this equation in a natural way.
Well, I cannot answer because I knew.
Yeah, I know, but only one.
No, there are many natural constructions that
Yeah, I
produce
think
this
so
equation.
because Tony, because you know, it's nice to know Virasoro algebra.
Yes.
You know Virasoro algebra, you can discover. You
Yeah.
don't know PDV, you can discover.
You can discover.
Yeah. You could guess the equation. But I thought the question was, if you knew the equation, could you guess the...
No, no. You know the equation you just told me. The question is if you had. Well, I think Victor answered it.
Yeah. Given a certain Hamiltonian operator, you can construct many equations associated to it.
Regular important in the loop important. One. Zero,
So
one.
that's more complicated.
Yeah,
A simple formalism would somehow suggest that you could write down integrable system.
From Virasoro, huh?
So, in fact, this simple fact that the same equation can be written in two different Hamiltonian forms is the key for proving it's one way to prove its integrability. And this is based on the so-called Renard scheme of integrability. So, by definition, we say that two Poisson vertex algebra structures on V are compatible. compatible if any their linear combination is again a Poisson vertex algebra structure. And then we have the following theorem, which helps us prove integrability. This is the so-called Leonard scheme. So suppose the following assumptions. First of all, V is a normal algebra. Algebra of differentiable functions. This was defined in the previous lecture by Victor. And anyway, it's not really an important assumption, because even if it's not normal, you can always normalize it, so go into a bigger space. And suppose that you have two compatible Poisson vertex algebra structures. On V. Suppose, moreover, we have a certain non-degeneracy condition on the second Poisson vertex algebra, which is a very weak technical assumption, which I'm not going to even to write it down. It's most of the time very easy to check and very.
What means that the kernel of the bracket is empty or what?
Okay, let me write it down. It says the following. So we denote u lambda u du. We denote it k of d. This is a differential operator. And the assumption says the following: that if k of d, df of d, k of d is equal to k of d, df star of d, k of d, for some f, then
For some more play.
df is equal to df star. This is the assumption.
So in the case of one function, it suffices that k of d is not zero.
Exactly, yeah. So suppose, moreover, that the same evolution equation can be written in two different Hamiltonian forms. If we have two Hamiltonian functions such that the equation associated to h and the local function at h0 is the same as the equation associated to k and the local function at h1, as for example we have for k dv. This is the key fact. And then suppose, moreover, we have a certain orthogonality condition. Which is also a very technical assumption, but it's less weak. It's a stronger assumption, which is the following. The orthogonal complement to the variational derivatives of h0 and h1 is inside the image of k. And what do I mean by orthogonal complement? Well, there is a natural pairing of v to dl cross v to dl to v mod dv, simply given by PQ goes to the integral of P times Q. And this is the orthogonal complement with respect to such pairing. Then, these two Hamiltonian functions can be extended to an infinite sequence of commuting local functions. Such that integral of Hn H is the same as integral of H n plus 1k, and moreover they are all integrals of motion. Whether you take H or K is the same, they are all commuting with respect to both Lie brackets. So in particular, we get a hierarchy of Hamiltonian equations. Du dtn equal the integral of Hn u, for example, with H. This is a hierarchy of Hamiltonian equations which are compatible, namely the vector fields are commuting and the Hamiltonian equations are in involution. And so they're all integrable. And so for KdV, all these assumptions are immediate to check. For example, let me prove orthogonality, which is very simple. For KdV, better not to start with these two, otherwise orthogonality doesn't work. So I will call this H1.
Talk about H0, which is U.
Yeah, I will call this H1 and this H2. And I will introduce H0. I start from a previous step.
This looks symmetric. I don't. So you're saying it's not symmetric.
Say it again?
You're saying it's not symmetric in swapping H and K? Can you put, instead of 1, you can put the H replaced by K?
It's not symmetric. The scheme, if you switch H and K, the scheme doesn't work.
Oh, looks like it should.
No.
Oh, that's because of the first equation.
Yeah, exactly. It gives an alter in the scheme. So let me discuss for KdV. Well, clearly, this assumption holds because I said it before. We have a compatible pair of Hamiltonian equations, of Poisson vertex algebras, which are this and this. And I didn't say it, but they are compatible. And then let's just check orthogonality. So we have to take the following H0 and H1. Integral of H0, we take U. And the integral of H1, we take U squared over 2. One also has to check this identity. This identity for such H0 and H1. Say it again? Okay. And let's check orthogonality condition. Well, we have to take the orthogonal complement to the variational derivative of H0 and the variational derivative of H1. This is clearly inside the orthogonal complement to the variational derivative of H0. Something is orthogonal to both, is also orthogonal to only this. And the variational derivative of H0, well, in this case, it's a function only on U, so it's the same as the usual derivative, which is 1. So we are asking, what is orthogonal to 1? What is a function f such that integral of f times 1 is equal to 0? Well, such a function means that it's a derivative. This is the same as saying that f belongs to the image of D. So this orthogonal complement is the image of D, which is exactly K. This is exactly K of D. So the orthogonality condition holds. Okay. I wanted to discuss briefly another
I
example.
presume you can compute these HRs.
Yeah, there is a very simple algorithm to compute all of them. Let me explain it briefly. I'll do it here. You start with your integral of h0 and integral of h1. Then you take variational derivative, and you get dh0 du and dh1 du. And then we know that if we apply h to f0 or k to f1, we get the same answer. It's written here. If you apply h to h0 or k to h1, we get the same answer.
So the orthogonality condition would provide you local functionals, yeah, the locality.
Yeah, so you can solve.
You can solve it.
Yeah, it allows you to go to the next step. So if you apply h or k, we get the same answer. Okay? And then we can apply h to f1. And then using the orthogonality condition, you can say that this belongs to the image of k. So you can write it as k of d of something, which we call f2. Okay? So you can find a certain f2 such that when you apply k, you get h of d f1. And you can find by inverting k, since it's in the image of k. Moreover, by the theorem, such f2 is a variational derivative of something. And so you can find the preimage of the variational derivative. And you find the integral of motion h2. And you keep going. You apply h to this, and you get h of d f2, which is in the image of k, so you write it as k of d f3. And then you invert k, and you get f3, which is a variational derivative, and you get h3, and so on. This is the algorithm to get all the integrals of motion. Okay, I wanted to discuss another example, but which is also similar to KDV, but I don't have time. So I want to say another thing, which is these Hamiltonian equations associated to Poisson vertex algebra are only part of the story. There are other Hamiltonian equations which are not associated to Poisson vertex algebras, and which are
So-called KDV hierarchy.
yeah, of course. There are Hamiltonian equations which are associated to what Victor calls symplectic operators. So let me remind you what is a symplectic operator. In the language of lambda bracket, it's a lambda bracket, a symplectic structure, let me call it. A symplectic structure is a lambda bracket on V, satisfying axioms very similar to the ones of Lie conformal algebra, namely sesquilinearity, skew symmetry, and instead of Jacobi identity, we have the so-called symplectic identity. which Victor wrote it before but with a different notation. Ui lambda uj mu uk minus uj mu ui lambda uk plus ui lambda uj lambda plus mu uk equals 0 for every I, j, k. And so this is the symplectic structure. I have to tell you what is u lambda something. This is what Victor before called the, did you call it Beltrami bracket? No. Anyway, it's this representation of the trivial conformal algebra on the algebra of differentiable functions. U lambda f is sum over in, the f du in, sum over n, lambda to the n. Okay, and so it turns out you can define a Hamiltonian equation associated Do we have color shock?
Down below, just at the bottom.
Oh. You can define the Hamiltonian equation associated not to a Poisson vertex algebra structure, but to a symplectic structure. And to Hamiltonian functional integral of h, which has the property that dh du let me associate to any symplectic structure a certain differential operator as we did before. Ui duj is sji of d. It's a certain differential operator associated to this symplectic structure. And so dh du should be such that this is equal to s of d applied to a certain element of v to the L. Okay. And so a Hamiltonian functional associated to a symplectic structure and such a Hamiltonian functional is an equation of this form. Du dt equal pi, where p is this. We can also talk about integrals of motions in the same way. We have the analog of the basic observation. I write it here. We have the analog of the basic observation. Is that the space of Hamiltonian functionals is a Lie algebra with Lie bracket integral of A f integral of G is equal to the integral of P times dg du, where this P here is such that, associated to a certain structure, symplectic structure S, where this P is such that S of dp is df du. It turns out that this is a well-defined Lie algebra bracket on the space of Hamiltonian functionals. And so we can define what is an integral of motion. For such a Hamiltonian function, which is a Hamiltonian functional So by Hamiltonian functionals, I mean local functionals which are such that their variation of derivative is in the image of S, this property. So it's a Hamiltonian functional integral of f, which is constant. And the certain Hamiltonian equation is integral if there is an infinite sequence of integrals of motion. So in the same way as we did for Hamiltonian function equations associated to Poisson vertex algebras, we can introduce the Léonard scheme also for symplectic structures. So suppose we have two symplectic structures, S and T, two symplectic structures on a certain algebra of differentiable functions, which are compatible. Well, now compatibility is which means something. I mean, I'm not going to say what it means. In fact, it's a certain identity similar to this, which involves both S and T. And the theorem is the following, that suppose again you have a normal algebra of differentiable functions, you have two symplectic structures, S and T, which are compatible. They satisfy a certain non-degeneracy condition, which again I'm not going to write what it means. But also, this is always a very weak condition, very simple to check. And suppose you have two Hamiltonian functionals such that, so let's say that dh0 du is S of d p0, and dh1 du is T of d of the same P. This is the analog of the relation between P0 and P1 before, Hj and H1 before. So this condition exactly means that you can write the same Hamiltonian equation in two different Hamiltonian forms associated to S and T, into these two Hamiltonian functionals. Suppose, moreover, you have the orthogonality condition. It's in the image of S. Then there is an infinite sequence of Hamiltonian functionals in involution, and so you get integrability of the Hamiltonian equation. And as an example, we can apply to what Victor called before the Kn equation. But let me just write the equation, and then I let you figure out all the details. Du dt is u triple prime minus 3/2 u double prime square over u prime. And it can be written in two different Hamiltonian forms with the symplectic operators that Victor wrote before. So I don't have to write them again. And using this fact, you can check all the assumptions of the Léonard scheme and you get integrability. Okay, I stop here. Just as a last observation, there is a more general setup which includes both the Hamiltonian, the Poisson vertex algebras and the symplectic structures, which is what is called Dirac structure, but I'm not going to say anything about it. Thank you.
Thanks very much. Questions? So there are these classical W algebras, the affine variety, which are Poisson vertex algebras. One natural question is whether you can associate integrable hierarchies to all of them or not, or whether they are bi-Hamiltonian or not. To some extent, this question was studied 15 years ago in the context of the inverse of type construction of hierarchies. Do you think that with this new formalism you can maybe answer this question, or did you consider this?
I think so, but it's kind of work in progress. So we ask the same question, but we don't have an answer yet.
Because we have some partial answer 15 years ago.
Right, right.
This sort of vaguely, this compatibility vaguely reminds me of shift of arguments, which is also a way of getting a complete set of commuting operators. Relation.
So I'm not sure about completeness. Commuting, yes, but I don't think this can tell you anything about the completeness of the set of coordinates.
Well, at least lots of
lots
commuting guys, but by, well, thereby, as it were, differentiating the invariants. But there's also some technology of having compatible, I don't remember it exactly, compatible Poisson brackets. That, and it's sort of looks a bit similar. I don't know if there's any.
I think it's more or less the same.
No further questions or comments? Alberto, once again, thanks very much.